Okay, thank you, Jim, and thanks to the School of Engineering for this very exciting evening. So, like Jim said, I'm Fei-Fei, and I work in computer science, especially in the area of computer vision. So, let's just start tonight with a question. What does the future world look like? I'm sure every one of you here sitting in the audience will have a picture of the future world in your own imagination. Here's one child's rendering of the future world. This young artist had a beautiful idea that parents are on a movie night out and very friendly robots are cleaning the house, cooking the dinner, and bathing the child. Note that the kid is actually happy and smiling, so don't we all want that? So I want you to look at this picture and think about one question. Have you ever noticed that in our imagination, robots all have eyes? Why does it need to have eyes, right? It doesn't necessarily have to. So one simple answer would be that this artist is only 7-year-old, and in all his or her life, he's familiar with animals and humans, and we all have eyes. So it's natural robots have eyes. But maybe there is some deeper answer to this. So to answer this question, let's just imagine a scenario in which that the robots don't have eyes. What would happen to them? So we haven't built these amazing robots yet, but we might have something close. So here's a robot that most of you know. It's called Roomba. And Roomba is almost as good as the cleaning robot. And it does go around and clean our room. So now let's take a look at the scenario and see what's happening to this Roomba. All right, so this poor Roomba, if it were to have a very simple visual system, it might probably have realized it's stuck in a corner of the room and there is a much bigger open space it can go to. But without eyes, it's stuck. So we still haven't answered the question, why vision? But at least I think this is a good example to show you that vision is important. Now let's get more serious and get some inspiration from nature. So I actually have here a very small fossil, and it's too small for most of you to see, so I enlarged it. And this fossil comes from more than 500 millions of years ago, and it's called trilobites. So for hundreds of millions of years, our Earth was filled with these simple animals. They are soft-bodied. They are simple, consisted of not too many cells, and they just float around. And they eat when some kind of food come crossing their path, and life was very mellow. And 543 million years ago, something happened. And that's what people call Cambrian explosion. And this is a very interesting time. In the sense of evolution, it's an astonishingly short period of time. And within this period of time, animals diversified, and the number of species just exploded to the point that evolutionary biologists call this the Big Bang of evolution. The Big Bang of evolution is still today the biggest mystery, one of the biggest mysteries in evolution, and there are many theories proposed to explain what happened. Why 543 million years ago, suddenly animals just diversified? So one of the leading theory, and to me the most convincing one, was proposed by an Australian zoologist called Andrew Parker. Andrew Parker conjectured The Cambrian explosion is triggered by the sudden evolution of vision, which set off an evolutionary arms race where animals either evolved or died. So the idea is that vision fundamentally changed the behavior of animals. Before that, these trilobites, they were just floating around and catching food. Now suddenly, food seeking is a proactive act or behavior. So predators have to go out and get food, and prey have to go around and hide away from the predators. So vision changed nature and evolution, and the rest is history. So I believe just as visual intelligence is important to nature, it is a cornerstone of all intelligence. Especially today, we're here to talk about artificial intelligence and the field of computer vision. Computer vision is already and will be shaping our lives and society. Almost every aspect of our life is being impacted by computer vision. You can think of entertainment, outer space and deep underwater exploration, personal robots, healthcare, medicine, surveillance and security, assistive driving, industrial robots. Every area and every technology is taking advantage of computer vision technology. So let's first talk about what is seeing evolving, why I think it's exciting, and more importantly, what's so challenging about it. What are the challenges my students and I have to face, as well as many computer vision scientists, when we design visual intelligence systems? So the first section I'm going to get into today is seeing is challenging. I think the monster's illusion is a very good illustration of the challenges of vision. So our world is fundamentally 3D. But the projection of our 3D world onto your retina or onto a picture is 2D. So you have to figure out, be it a brain or a computer, has to figure out what's going on between in this 3D world by using a 2D image. That is the fundamental challenge. That is why in this illusion, the two monsters are actually exactly the same size in pixel areas. But your brain has worked its way out to understand the 3D world. So you have to infer these are this is one big monster chasing a small monster. And this is an even more striking and peculiar visual illusion to illustrate that our brain worked very hard, sometimes too hard, to interpret the world. So you see a checkerboard, and you see block A and block B. If I tell you, trust me, block A and block B are exactly the same grayscale. No, you laugh. You won't trust me. I'll block off most of the scene. Okay, let me go back. Block A and block B are exactly the same grayscale. Don't believe it. Yeah. So let me just repeat. Vision is very challenging because our 3D world is cluttered, full of objects, and they occlude each other. Much of vision is involved in interpreting and inferring this 3D world based on limited information, which is a 2D imagery. So it took more than 500 million of years of nature to design and develop the most powerful visual intelligent machinery in the universe, which is our human visual system. So it's no surprising that I tell you that more than half of every one of your brain is involved in vision. It is by far the biggest sensory system in your brain. And we need all this resource to do this very challenging task. So compared to evolution, the field of computer vision is very, very, very young. In fact, It started on July 7th of 1966. This is a true story. In 1966, some professor in artificial intelligence lab at MIT has figured that AI has advanced so much by that time, we can use one summer and hire a couple of smart MIT undergrads and figure out and build a visual system. That was the summer project. They probably got some money from somewhere and thought they would get it done in one summer. Luckily, at least for me, that didn't happen. And almost 50 years later, our field is thriving and growing, and we have many, many bright young people working in this field. So really, for the rest of this talk, I'm going to go through very briefly a journey in the past 50 years in 5 minutes about what has happened in computer vision and by showing you a few work from my lab. So what are the key components of building a visually intelligent machine? First, I think we need to recognize objects. Objects are building blocks of our world and building blocks for visual intelligence. So in fact, one of the pioneering work of object recognition was started here at Stanford by a group of pioneering roboticists and computer scientists. And you can see back in 1979, object recognition was very simple. It focused on these line drawings of simple objects, mainly to just illustrate the idea and prove the concept. So let's just fast forward about 2 to 3 decades. In modern days, we computer vision scientists work with real-world pictures and try to recognize objects in these real-world scenes. For more than 10 years, shortly after the turn of the 21st century, our field has been working with this very important dataset called Pascal VOC dataset that consists of 20 object classes. And annually, our field, computer vision scientists will get together and evaluate different algorithms and see how much progress we have made. And that plot shows you from 2009 to 2012, we have made quite a bit of progress. But around that time, that was around that time I became a professor, and I become very unsatisfied with this number 20. How many objects are there in the world? I don't know, but I know it's more than 20 because I have more than 20 objects in my office. Granted, it's a bit cluttered. So it could be, in a dictionary, there are tens of thousands of nouns. But if you look at, let's say, eBay catalog or Flickr tags or Wikipedia pages, all of these numbers are bigger than 20, a lot bigger than 20. So one of the projects we have done in our lab is really to rethink about object recognition in real-world scale. We want to take the number 20 and go into tens of thousands of object classes and millions of images. This is a large-scale project we have done called ImageNet, in which we collected more than 50 million real-world photos across 22,000 object classes. And we start to develop visual recognition algorithms at this scale to test object recognition. Without getting into the details, one of our work is a demo called EVA, in which that EVA can take any objects or pictures of objects and try to label it without making any mistakes. And the idea is that if EVA sees a bird with different levels of confidence, EVA can either get to the very fine details and name it the subspecies of the bird, or can just stay around its comfort zone and try to recognize the generic class. Here's another example of EVA taking a picture of a funny little dog in a car and labeling this picture with more than 70% confidence that it saw, more than 80% confidence it saw an animal and rear view mirror. And here are more examples of EVA. So let me try to move fast and talk about the next topic. So beyond generic objects, I think seeing involves recognizing people. People are just fundamentally important. In fact, neuroscientists have discovered there are specific brain areas devoted to people recognition, such as face areas, as well as body areas. And also, our field, one of the earliest technology success or industrial success story of computer vision is face detection. In 2001, Viola and Jones published this very seminal paper on real-time face detection. 5 years later, Fujifilm rolled out the very first digital camera that has face detector in it. Today, all of your digital cameras and smartphones have face detector, and that is a technology developed by computer vision field. So in my lab, we have been looking beyond just face detection, but looking into understanding human behaviors, such as human action recognition and classification. We have also taken cameras into the real world and into the, for example, busy train stations, and try to track hundreds of thousands of people per day and millions of people per year and watch their behaviors. So people watching is very important. Last but not the least, to see is to tell the story of the visual world. That is really the holy grail of computer vision. A picture is worth 1,000 words. This is an experiment I conducted as a grad student a few years back, where we show human subjects a picture for a very short amount of time, as short as, let's say, 500 milliseconds. That's half of a second. And you ask them to type everything they see. So if you pay them enough, they'll type 1,000 words. But even if you don't pay them enough, they still type a beautiful story. So if you think about what I just showed you, we said that computers today were working on object recognition, we're working on people recognition. If computers have solved object recognition and people recognition, what story would computer have typed? Well, not much, actually. You know, compared to what the human can give you, this is how much object recognition and people recognition can give you. So the rest of our work these days is to focus on the richer story of the visual scene beyond just simple object labeling and human tracking. For example, we work on recognizing human-object interactions. We label a picture not only by the person, by the action, but also the pose of the person, the object it's interacting with. We also work on what we call total scene understanding, where we take the image and we try to label every single image and every single object, as well as the overall event and so on. So these are all towards the more holistic scene understanding and storytelling. We also work on videos and try to tell stories beyond just, okay, I label an object, but look at social roles and social events. These are all automatically recognized by our computer vision algorithm. And so we have made some progress towards the storytelling of visual things. So we went from 4 labels to a few more, but there is a lot more to be done. And this is really, for the future work, I think that one of the most exciting areas of computer vision is to reason with visual and multimodal knowledge. This is something that Chris Manning will actually mention a little bit later. So, well, that was a very quick overview of the field of computer vision. We're a very young field. It's less than 50 years, but we have been working hard to figure out some of the key components of what it means to see. And I hope that next time you see a picture of a robot, you can ask the guy next to you, what do you think the robots have eyes? We have an answer for that. So thank you very much. This is my lab.